Well, good morning. Let's go ahead and call ourselves to order. Thank you all for attending today. It's a real honor to be hosting, if you will, a celebration of the 75th anniversary, the celebration of Cp1. So we're very excited. We've got a full day planned and a lot of fantastic dialogue, I'm certain, will occur throughout the day. So I'm Paul Kearns, the Interim Laboratory Director here at Argonne. I'm very pleased to extend a welcome. I want to thank everybody for participating in the symposium to mark an important milestone in the history of science and history and the national laboratories, particularly Argonne. Had breakfast this morning with Nigel Locklear. Nigel's here, and he directs a Fermi lab, but this is actually Fermi's lab, and so we're very pleased to celebrate, if you will, the 75th anniversary of Chicago Pile 1, so we're pretty excited about that. I want to extend a special thanks to our speakers for helping guide today's conversations and especially acknowledge our guests from the Department of Energy. We have Steve Binkley, Director of the Office of Science. I'll provide Steve a more formal introduction in just a minute. Ray Furstenau, who is the Associate Principal Deputy Assistant Secretary for Nuclear Energy. And we have Joanna Livengood, Manager of the Argonne Site Office. So we're pleased to have DOE here as well. I also want to take a moment and really recognize the Cp1 Organizing Committee for all their efforts. They put together a fantastic program and really done a great job in getting us here today. Linda Young is the chair. Linda, please stand up, Linda. Please, thank you for your hard work. Good. Jeff Binder, Roger Bloomquist, Laurel Briggs, Un Chang, Robert Rosner, Lynn Soderholm, and Richard Wilson. So let's give them all a round of applause at this point in time. They've done a nice job. As many of you know, Argonne owes its very existence to Enrico's Fermi discovery. This lab was formed with a single mission, developing peaceful nuclear energy program. From there, we've grown into a multi-program science and technology laboratory, certainly from our roots, if you will, in physics, materials, and chemistry. We've added to that a great deal, but we're forever recognizing and conscious of our roots and really have built on those to build the laboratory we have here today. As you'll hear from today's speakers, Argonne and all the national laboratories are a vital part of the ongoing nuclear energy conversation, with the percentage of the nuclear in the international energy mix forecast to increase by 9% by 2040. The conversation certainly remains relevant at home and abroad. Like they always have, the national laboratories continue to lead the way in verifying the safety and sustainability of existing nuclear systems, innovating next-generation nuclear technologies, including reactor and fuel cycle design, and developing future R&D infrastructure for nuclear technology, including a new fast test reactor. To support these sentiments, I am honored to share with you a letter addressed to myself, Mark Peters, Director of the Idaho National Laboratory, and Thomas Zachariah, Director of the Oak Ridge National Laboratory, signed by each senator and congressional representative from the district and home states of each lab. So bear with me, if you will. The letter is about 5 paragraphs. It'll be a quick read, and I'm going to walk through it because it's really well written. It says, Dear Dr. Kearns, Peters, and Zachariah, congratulations to the U.S. Department of Energy's Argonne, Idaho, and Oak Ridge National Laboratories as they commemorate the 75th anniversary of Enrico's Fermi historic achievement in nuclear physics, a landmark accomplishment that led to the founding of the national labs, decades of pioneering discoveries and peaceful uses of nuclear technology, and our nation's leading source of clean energy. On December 2nd, 1942, Fermi and his colleagues at the University of Chicago demonstrated with Chicago Pile 1 that a nuclear chain reaction could be initiated, sustained, and controlled. That day changed the course of history, setting in motion continued achievements throughout the laboratory's histories, including major achievements in scientific understanding, human health, and energy development. Cp1 launched the fields of nuclear physics, radiation biology, nuclear chemistry, nuclear power generation, with Argonne, Idaho, and Oak Ridge National Laboratories all playing pivotal roles in the development of current generation advanced power reactors. As the U.S. considers how to meet the country's energy needs, the labs remain crucial partners with expertise on safely operating and extending the lifetime of current generation reactor plants and designing next generation nuclear reactor systems. We proudly commend the laboratories' integral role in the advancement of science and the innovation and development of new energy technologies to address some of our most complex societal challenges. The national laboratories are the crown jewel of the United States scientific community, and we thank the laboratories for sustaining essential expertise in nuclear technologies that is vital to our nation. Again, we are proud to support your achievements as we celebrate and commemorate Enrico's Fermi historic achievement and the ensuing distinguished histories of the Department of Energy's national laboratories. Again, it's signed by the senators from each of the states as well as the congressional representatives. So very nicely done. Thank you for allowing me to read that to you. Today we have a unique opportunity to learn about the state of the science and technology in nuclear energy and get a glimpse of what the future could bring. As we kick off today our contemplation discussion, I'm pleased to introduce our keynote speaker. Steve Binkley is the Acting Director for Science Programs in the DOE Office of Science. Steve is a senior career science official in the Office of Science, the third largest federal sponsor of basic research and primary supporter of physical sciences in the U.S. Steve provides scientific and management oversight for the 6 science programs of the Office of Science: basic energy sciences, biological and environmental research, fusion energy sciences, advanced scientific computing research, high energy physics, and nuclear physics. He brings to the office an extensive leadership experience with the national laboratories and DOE, as well as other federal agencies, including the Department of Homeland Security. Steve is also a renowned researcher in his own right in theoretical chemistry, material science, computer science, applied mathematics, and microelectronics. Please join me in welcoming Steve, please.
Okay, can you hear me in the back? Okay? Sound check? Okay, good. Let's see. First of all, I'd like to thank Paul Kearns, Acting Director, for the very nice introduction, and also thank the Argonne National Laboratory for the opportunity to be here to speak to you today. It's actually very much an honor for me to do this. I think it's probably the first time as a physical chemist I've given a talk on nuclear energy, so we'll see how things go today. I know I'm surrounded by a lot of expertise in this area, so we'll see how it goes. I'd also like to thank the University of Chicago and Eric Isaacs, with whom we've worked very closely with over many, many years in the stewardship of Argonne National Laboratory, which is one of the laboratories that is very important to the future of the Office of Science and has been a pioneer in several areas of physical sciences that are very important to our programs today. And then also I'd like to acknowledge Joanna Livengood, who's our on the site office manager. Joanna has the day-to-day responsibilities for overseeing the federal activities here at the lab. Let's see, what I'd like to do first is talk a little bit about why we're here today, which is the acknowledgement of the 75th anniversary of the Cp1 reactor. And I personally am somewhat of a student of history. I've spent a fair amount of time both at DOE and even before I came to DOE trying to really understand how the country got to where it is with respect to the Manhattan Project and the nuclear weapons program, and then nuclear energy technologies and so on. And you know, there was a very, very dramatic period in the late 1930s running up into the 1940s. A number of very, very significant developments occurred, both in science as well as in technology. And CP1 is definitely one of those signal events that occurred during that period of time. And you know, just briefly, in terms of the historical context, recall that Lise Meitner and Otto Frisch had published their theoretical interpretations of the Hahn-Strassmann results and had essentially identified nuclear fission. That occurred in February of 1939. And for most scientists who really thought through the implications of that discovery, they realized that it had very, very far-reaching implications, which in fact culminated in the letter that Albert Einstein sent to the president in October of 1939, highlighting the possible weaponization possibilities of that discovery. Obviously, 1939 was the run-up to World War II. You talk about stressful times in a nation. The U.S. was very much in turmoil at that time. And the concerns that the German government would be able to develop nuclear fission in any weaponizable form was something that was very sobering, I think, to many, many of the scientists of that day. The Manhattan Project was set up, and Leslie Groves became the director of that in September of 1942. So think about all of those things as kind of the backdrop for the activities of Enrico Fermi, who led the development of the Cp1 reactor, which was then demonstrated at the University of Chicago campus. Some of the statistics about the reactor are given here. It's interesting that it was done by a team, which was already then becoming a characteristic of how DOE projects would be run historically. If you read through this list of names here, this is only a partial list of the 50, but this really reads like a who's who of science in the 1930s, 1940s. And in fact, you can pick out several future national laboratory directors from this list. Of interest was Leona Woods, who was the only female member of the team, and she also was the youngest member. So even this early on, women were making their way into this area of activity. This bullet is somewhat understated. After the demonstration was successfully completed, Arthur Compton, who was one of the team members, had a side-channel conversation with James Conant, who was the director of the National Defense Resources Council at the time. And if you remember, or if you've looked at the history of the NDRC, it was that body that eventually ended up overseeing the Manhattan Project, developments like radar, the bomb fuses, and so on. All of those activities were coordinated out of the NDRC during the World War II period. And in the case of the Manhattan Project, it was conducted at such a high level of secrecy that only very few people in the government at all knew of the Manhattan Project. And this private communication between Arthur Compton and James Conant was there to signal the success of the activity. If I remember the history correctly, he said something like, "The Italian navigator has landed," was the catchphrase that was used to communicate the success of the experiment. Very, very modest power level, et cetera. I mean, the real accomplishment here was demonstrating that it is possible, or was possible, to have a self-sustained fission reaction. Sticking with the historical context and then moving forward to the next few years, the Atomic Energy Act was passed in August of 1946, which set in motion the whole production complex and the national laboratory structure. And then in the Atomic Energy Act already, the original version, there was a very, very strong focus on the development of nuclear energy for civilian purposes, which is, I think, a very important accomplishment at the time. They could have easily circled the wagons and had a very much only security focus. But nevertheless, the framers of the Atomic Energy Act realized from the very beginning the importance that nuclear energy would have worldwide. Eisenhower gave his now famous speech, Atoms for Peace, at the UN in December 1953. The Atomic Energy Act was amended in the following summer, basically. The amendments didn't have much to do with the Atoms for Peace part, but actually focused more on aspects of civilian control of nuclear weapons. And then there were two UN conferences on peaceful uses of nuclear power, one in 1955 and one in 1958, which essentially began to pull world interest together for peaceful use of nuclear power. One comment I would make regarding the second one of these conferences is that it was in the second UN conference in 1958, and in the run-up to that involved the declassification of thermonuclear fusion aspects of energy production, and the international fusion activities that exist today grew largely out of the second UN Conference on Peaceful Uses, which is in 1958. I also find it interesting to go back and look at what the Atomic Energy Commission looked like in that period of time. So if you look at this slide, this is actually an org chart of the Atomic Energy Commission taken from December 1948. So if you recall from the first slide, this is approximately 2 years into the Atomic Energy Commission. And, you know, as you would expect, you can find the weapons program, let's see, where is it? Division of Military Application, which was essentially Los Alamos at that time, and then, in fact, all of it was at Los Alamos, and production activities related to that. There was an extant production office that was set up for the production of materials for the weapons program. And then even as early as 1948, though, there was this piece over here referred to as the Division of Research, which was essentially the early stages of what is now the Office of Science. Also, I find it also interesting that in that same time frame, there was already a Division of Biology and Medicine. Again, recognition that nuclear technologies would have an effect on biology and also ultimately on medicine. And this office existed as far back as 1948. Stepping forward approximately 23 years to December 1971, this is the structure that the Atomic Energy Commission had at that time. Remember now, this is approximately 2 years before the oil crises of the 1970s. So this is essentially pre-oil crisis. Again, the focus is really on nuclear energy, nuclear power, et cetera. Again, you know, demonstrable part that's focused on national security activities. This has been fleshed out to include naval reactors, et cetera. And then the science part, what was to become essentially the Office of Energy Research a little bit later on, and then ultimately became the Office of Science, is in this box here. And the part of the Division of Physical Research was the part that contained essentially the materials chemistry, particle physics, and nuclear physics programs. And then also in this time frame, the biology and medicine activity that was on the previous slide has moved in under this same category, as well as the fusion program that I alluded to a little bit earlier that came out of the second UN conference. There's also, by 1971, a part of the then commission that's focused on reactor technology development, applied technologies, and space nuclear. You know, this is essentially the precursor elements of what would become applied energy programs. Now, it's also important to keep in mind that going back a second here, that in this run-up from the late 50s to present day, which involves essentially getting to a fleet of approximately 100 reactors across the US at 61 sites. The technology of those reactors are predominantly BWR, boiling water reactors, or PWRs. Pretty much standard technologies. And a lot of the effort that was expended in labs like Argonne and Oak Ridge, et cetera, were oriented towards those technologies. However, you know, there was also, going all the way back to the 50s, quite a bit of effort in labs like Argonne and Oak Ridge focused on advanced reactor technologies, and to include molten salt reactors, gas-cooled fast reactors, other fast reactor concepts. And one of the hallmarks of the early Atomic Energy Commission work was to begin to look at advanced reactor concepts as well, in the hopes that they could essentially find a role in the commercial marketplace. Stepping aside a little bit and then looking within the Division of Physical Research, which was one of the predecessor parts of what is today Basic Energy Sciences, you can find references to nuclear technology and essentially science in support of nuclear technologies that was conducted within the Division of Physical Research. This is an excerpt from the summaries of basic research programs in metallurgy, solid state physics, and ceramics that was published in the 1961 compendium of the summaries. I don't know how many people in the room remember the dreaded summaries that had to be prepared every year. I personally do remember them. It was quite a bit of an effort every year to prepare summaries that went into a paper document. There were research activities in this particular case looking at production and treatment and properties of materials, physical research, nature of matter, and also importantly, interaction or radiation with matter by various means. Here is an excerpt from one of these research summary documents that actually lists specific activities that were underway in the early 60s here at Argonne National Laboratory. There's a fair amount of work on uranium and plutonium properties, physical and chemical properties of graphite, which obviously had important uses in reactor technologies. There was also the beginning of studies in X-ray and neutron diffraction studies, metallurgy of uranium, plutonium, et cetera, radiation effects, other research in low temperature physics. Again, these are all drawn from Argonne examples. Then in 1973, there was another watershed event in the history of the country, namely the oil embargoes that occurred in 1973, and then the subsequent oil or energy shortage problems that occurred in 1979. And I don't know about y'all in the audience, but I was actually at Carnegie Mellon in the 1973 timeframe, and I remember this quite well because in Pittsburgh, Pennsylvania, where I went to graduate school, there was rationing of gas, and in fact, there were periods when one could not get gas at all. And so this had quite a dramatic effect on at least the areas that I lived in. This led in fairly short order to the establishment of the Energy Research Development Administration, ERDA, which was established in 1975. And then after a fairly short existence, ERDA was mapped over into what is today the Department of Energy, which was established in 1977. There have been a few other refinements to the Department of Energy since 1977, most notably the passage of the National Nuclear Security Administration Act in the early 2000s and the Energy Policy Act that was passed in 2005 that gave rise to the Undersecretary for Science position in the department. This transition that started in 1973 had a pretty significant effect on reshaping R&D priorities across the then administration and then ultimately the Department of Energy, leading to essentially improved use of fossil energies, expanding non-fossil energy R&D, expanding into solar, renewables, energy efficiency, et cetera. And then importantly from the science side, the physical sciences research that was conducted inside what was to become the Office of Basic Energy Sciences was expanded significantly into non-nuclear energy technologies. So it didn't diminish the nuclear related so much, but it did allow for research in non-nuclear energy technologies. Looking inside what is currently the Office of Basic Energy Sciences, you can see this pretty clearly, but essentially through this transition process that I just mentioned, the Basic Energy Sciences program was focused really on physical phenomena relative to the goal of meeting the nation's energy needs. And so there have been a whole series of planning activities that have been conducted by the Office of Basic Energy Sciences over the years to support that mission. Some examples of research that have come out of that program deal with radiation damage, radiation-resistant materials, and so on. These are both examples of research that came out of the BES area. Further examples, a lot of focus on radiation effects, also looking at very practical problems like stress corrosion cracking and radiation-induced nanostructuring. Speaking from experience with Fukushima, I know there was a lot of concern during that period looking at stress corrosion cracking when the Japanese used seawater for the cooling. Another area that has been very important in the Office of Science portfolio is looking at heavy element chemistry, the transuranics. And in fact, the Office of Science is the only supporter in the US of basic research into the properties of transuranics at this point. There's also been pretty active exploration in the Office of Science, looking at different modalities of conducting basic research. Historically, the research activities in the Office of Science were really focused on principal investigator research, so the idea of essentially funding single investigators. Going back to the roughly 2009 timeframe, there was a concerted effort by my predecessor, Pat Damer, and others to develop several new approaches aimed at doing research that opened it up to essentially small groups of people, teams of people, larger groups of people in an effort to try to expand the impact of research. One such activity was the establishment of Energy Frontier Research Centers, EFRCs, which were first established in the 2009 timeframe. And as you would expect, even the EFRCs in that time frame were some of which were essentially chartered to do work that was nuclear technology related. Another area of basic research that's been very important has been to look at radiation effects at interfaces, which has impacts in looking at claddings like zircaloy, also looking at different fuel systems and coolants for future reactor concepts. This is work that is being carried out at the Notre Dame Radiation Laboratory. Now, to sort of wrap things up here and bring us up to date with where we are today, one of the hallmarks of basic energy sciences since the early 2000s was the use of basic research needs workshops to bring the community together in various areas to define priority research directions that the program would then follow in specific areas. And you can see the list here of basic research needs workshops that have been chartered since 2003 through 2016. And it's really quite a range of activities. There was, in the 2006 timeframe, a look at advanced nuclear energy systems. And going back over the last year, the leadership in our organization decided that it was time to revisit that with essentially a decade having gone by, it was time to go back and look at the basic research needs in the area of advanced nuclear technologies. And so the most recent one of these basic research needs workshops that has been conducted was August 9 through 11 and was focused on needs for future nuclear energy. You can see the charge here that the team was given to work against. The team was led by Kelly Bierschmidt of Idaho, Michelle Buchanan of Oak Ridge, Laura Clark of Washington State, and Ian Robertson of University of Wisconsin. The technical leads from the Office of Science were Linda Horton, who's the division director for the Materials Division in the Office of Basic Energy Sciences, and then John Betrano, who's one of the program managers working with Linda. The charge is listed here. There were breakout sessions as listed here. Typically these workshops, if you've never been involved, are very, very intense. They bring up to 100 to 200 members of a given community together for an intense 2 to 3 day period where they develop priority research directions, which we then use for planning purposes for the program. We've also, in the last several years, undertaken to do these basic research needs collaboratively with other program offices in the department. And so in fact, this workshop was actually planned and coordinated very carefully with the Office of Nuclear Energy in order to have essentially program buy-in from that office as well. Listed here is the priority research directions that came out of the workshop. There will be a published report forthcoming soon, but the priority research areas are listed here. You can see that it's looking at things like molten salt coolants and liquid fuels, which is certainly in the advanced reactor category. Looking at hierarchy of materials design and synthesis for complex reactor environments. Finding ways scientifically to essentially tailor and control the impact of, or tailor interfaces to control impact in nuclear environments. Looking at multi-scale evolution of spatial and temporal processes in nuclear environments. And then also identifying and controlling unexpected behaviors and rare events in cascading processes. We're in the process right now of digesting this information in terms of our planning process, and you can expect more to come of this as we progress. And I think at that point it would be useful to stop. I'd be glad to take any questions.
So thanks for that look in the past and also towards the present. I'm over here in the middle. I have a question about, nuclear power in the U.S. has these very old designs, and I think we're going to hear more about the various new designs that could be used. How closely is there coupling between what might be realistically commercially implemented and the research priorities that you have here?
So, I think that's a question that's going to come out of the discussions during the course of the day. focus of what I was trying to talk about was the basic science underpinnings going into nuclear energy technologies. And so I think I'll leave that till the rest of the day to see how that comes out.
Yes, so nuclear energy is a very international sort of field, and the research directions that you outlined, I'm sure have interest from abroad as well. Is there any coordination between what you would do and other countries?
Yes, you're definitely correct that the research interests that are listed there span the international context. And we do, in fact, have international agreements, bilateral, in some cases multilateral agreements to do research, joint research, collaborative research with various countries. And as we develop priority research directions like this, we then factor that into the types of agreements that we have in place today. And so, we presently have research agreements in place with a variety of countries, including countries in Europe, also countries in Asia, Japan, Korea, et cetera. And then countries that we're just, essentially negotiating new agreements with. For example, we just signed a new science and technology agreement with the United Kingdom. I guess that was last week. And one of the topics that they raised in the discussions we had at headquarters had to do with nuclear energy technologies. So as opportunities arise, we definitely plan to do coordination internationally.
So you didn't mention, I was sort of surprised at this given your background, the role of advanced simulation and the limits of simulation in a reactor design and issues.
Yeah, actually, there has been considerable progress in simulation in the nuclear energy area. In fact, the Consortium for Advanced Light Water Reactors, the CASTLE activity at Oak Ridge has been very successful in that regard. And I know there's been a significant amount of modeling activities done at Argonne and also at Idaho over the last decade. And, I think the importance of simulations in both reactor safety and reactor development is definitely on the rise. I can tell you, because of primarily time constraints, I didn't want to get into a computational talk as well. But we do have advanced fission systems and advanced fusion systems as applications in the exascale activity. And so, yes, definitely. I think there are plenty of opportunities for advanced simulation in this area.
Steve, I believe I get to ask the last question, and it really is about training up, if you will, future generation of not only researchers, but also others that might find employment in the nuclear energy and nuclear power field. Here at Argonne, we're very proud to have recently established what we call the Next Generation Society, which is really focused, if you will, on providing a networking opportunity and also needed support for our early career scientists and really thinking about that. And kind of interesting to note that the real, if you will, thought behind the idea and the early leadership for that effort really comes from our nuclear engineering division. And so it's kind of interesting to observe that, but also I thought you might want to, if you wouldn't mind, share your thoughts in terms of early career scientists and how, as a national laboratory system, the Office of Science can really help folks move along in terms of their careers.
Okay, thanks, Paul. Well, certainly, the development of next generations of scientists and engineers is a very critical problem in the U.S. This is something that you'll find a lot of discussion about in Washington these days, especially when you look at how rapidly China is moving in terms of developing its workforce. And so at DOE, we've been working very hard across several programs. I'll comment mostly on the Office of Science activities, but we do have an early career program that we are pushing along. Every year, we try to identify and recruit the best young people, early career people, to that activity. But frankly, training and retention of the best people is a major problem, not just in nuclear technologies, but across the board in the very, very high-end science and technology areas. There's intense competition for talent, and one thing that we do observe is that early career talent, as well as mid-career talent, is attracted to the best facilities and capabilities. And so it's important to keep in mind that correlation, that in large measure, people are attracted to either the hardest problems, the most challenging problems, the most rewarding problems, the problems where they have access to the best capabilities, best computing, best access to reactors, et cetera. And so, without continued investments in those areas, the U.S. stands to fall behind in training and retaining the highest caliber of the scientific and technical talent. When you look at what's happening in China with the very, very large population that they have, and they're able to put essentially more and more people through their system, which is ultimately, I think, going to give them a significant edge, unless we can find a way to keep not just keep the pace, but actually do better in the U.S. in terms of training the best possible people, and to really focus people on what it takes to innovate, what it takes to create new science, to create new engineering. I think that's one of the core strengths that the U.S. has. And so keeping the focus on that, I think, is really important.
Well, let's thank Steve again, please.